Check, 1, 2, check. Hey out there, if you're watching. Well, we've never tried this before, but this will be fun. I'll prefer to take questions, but I will go ahead and say that this is going to be a review over Chapter 14. And if there are no questions, I'll go ahead and start from the back. I'll start with 14.8, Section 14.8, and then work our way down to Section 14.2. So, or rather, maybe we should start with 14.7 and 14.8. So, optimization, unconstrained type, and the constrained type, where we might use Lagrange multipliers. And then we'll go back to limits and continuity, functions of, say, two variables. Okay. And I do have some questions prepared if you have no specific questions. But let me go ahead and check out the chat here. All right. So does anybody have any questions at the moment? Okay, so we are going to so 14. So we'll start with 14.7 and 8. How about that? Unless you have objections. Okay, so this is optimization, finding relative maxes and mins, and it's the what I would call the unconstrained case. And then we have optimization with constraints. So that's where we use Lagrange multipliers. All right. Okay. So let's I guess work an unconstrained case. And again, I'm checking chat just to see if you have any questions. All right. Okay, so this is I like this example a lot because it showcases how probably the most difficult part in the unconstrained optimization problem is finding your critical points, because you have a system of equations you need to solve. It's not necessarily linear. So let's start. Okay, so this type of problem would say something like, given this function, find relative maxes and mins, and wouldn't say very much else, meaning there are no extra constraints on what x and y can be. Okay. So find all extrema and saddle points, if any. So relative extrema. All right. And then we'll after we find the critical points, right? We'll then use the second derivative test to classify what happens at those critical points, if possible. So let me outline the problem, or the procedure for this optimization problem. Okay. All right, so the first thing to do will be to find the gradient of the function and set it equal to the 0 vector. Of course, what that amounts to is finding the partial derivatives of your function and then setting them equal to 0 simultaneously, which will then give you a system of equations in which you can solve for the critical points. I'll just label them CPs, critical points. So those are candidates in the domain of our function, at which we have maxes, mins, or saddles. Okay, so that's like really step one, right? Solving the system of equations. You might have to do some casework to solve the system. And then afterwards, we use the second derivative test to classify what happens there. So this is where we compute this what your book calls D, probably for determinate. Involves the second derivative. Some people remember it by saying it's like the second order partial matrix of second order partials. So, fxx, for example, means second derivative with respect to x, yeah? Or differentiate f twice with respect to x. That's supposed to be fxx, sorry. Then you have fxy, fyx, and by the way, if your function f is smooth enough, the mixed partials would have to be equal. And I don't anticipate anything else in your class. But it's this matrix of second order derivatives, its determinant, D, is in your book given by this formula, fxx times fyy. So it's this cross product, yeah, fxx times yy minus fxy. And it's, since those are mixed partials are going to be equal, that's essentially fxy squared. Okay, and then we remember that we will be evaluating this at the critical points. All right. So, 1 second. So then the second derivative test has the following criteria for classifying what happens at the critical points. So it'll say that if, well, let's think of it this way. This derivative, this determinant, evaluated at your critical point can either be negative, it could be 0, or positive. Alright, if D is negative, then right away we know that we have a saddle at that critical point. So we have a saddle. Okay, if D is 0, this test is inconclusive, not unlike how it was inconclusive, not how unlike the second derivative test was inconclusive for in one variable calculus, if you recall. Okay. And if D is positive, then we have an extrema that's either a relative max or min. And so to know which one it is, we have to look at fxx, so evaluated at our critical point. If that fxx is negative, then well, in one variable calculus, when our second derivative was negative, we knew that the graph of our function was concave down, and that meant that at this critical point we had a peak, a max, right? So then we can now conclude that we have a relative max at our critical point. And the last case is fxx being positive. Alright, so again, the second derivative being positive meant concave up, except in two variable calculus it's like concave up all the way around. So it's like paraboloid up, if you'd like. So that's a minimum. It's a low point there, clearly. It's a relative min. Alright, that was just a hopefully not too long of a review of the procedure for unconstrained optimization. So let me go ahead and copy the function here. Yeah. And let's apply this. Oops. Right. So our job is to find all relative extrema and possibly saddle points. So the first thing we did was simply differentiate the function with respect to x and then with respect to y. we found the first order partial derivatives. And I think to do this, I'll just go ahead and distribute the xy factor into the parentheses there. So I have xy minus x squared y. All right, and the last term. So let's differentiate term by term, first with respect to x. And then partial of f with respect to y. So, all right, so now we're going to take these derivatives and set them simultaneously equal to 0. Let me undo that. Oh well, okay. Well, let me just do it here. Okay, so we set the first derivative equal to 0 and the second one. And go ahead and try to solve the system, which is, I don't think this is easy, but I would just do some casework here. So for example, let's call this equation A, let's call this equation B. If I look at A, I see that y is a common factor, so I'll use the strategy of factoring one equation and then considering cases for when that product I get after I factor is 0. That's the first equation, right? So what can we glean from this equation? Well, this product is 0 as soon as one of the factors is 0, so this means that either we have the case where y is 0, or we'll have the case where the other factor, which is a little bit more complicated but not by too much, is 0. Okay. So once I have the case that y is 0 from the first equation, I can go to the second equation, which I labeled B, and then consider it with the restriction that, y is 0 in this case. So this allows me to set y equal to 0 and see what I get. We factor. How's my handwriting, by the way, huh? Yeah, I don't do this too often. Okay. So we see that here either x has to be 0 or x is 1. So, all right. So our critical points from this one case, there are two, right? And remember, our critical points are points in the domain of our function, so that's the xy plane. So we have x is 0 and y is 0, or x is 1 and y is 0, right? So what we have there are two critical points, and so we next want to find the remaining ones by considering the second case right there. All right. Okay, so the second case. All right. So, well, how do we deal with this? Well, this equation is at least linear in x and y, so I can solve for y. Oops, let me erase that. Right, so y is minus 2x. And once I have y in terms of x, I can go to the second equation, namely equation B. With, of course, the restriction that y is now 1 minus 2x, so we get to replace y. All right. Okay. Distributing and either factoring or using the quadratic formula, yeah? we get to know what x is. Alright, so we have 3x squared minus 3x. Oh, nice. That's pretty simple. So 3x is a common factor. Alright. Okay. Right, so here we see that this product is 0 as if either x is 0 or x is 1. But of course, if you we look up here, if we know x, this equation tells us exactly what y is. So x is 0, and in that case y is 1. And if x is 1, y is negative 1. Oh, so that's it. We found 4 critical points. Right. So at this point, we'll go to the second step where we'd like to classify what happens at these critical points. And for that, we'll need the second derivative test. So we need second order partial derivatives. Let me go grab the first order derivatives really quickly. All right. So step 2, I suppose. Okay, we'll go ahead and need to find fxx. So of course that means partial of f of x. I'm sorry, fx with respect to x. So we'll differentiate this with respect to x, and that yields negative 2y. And then fyy. So differentiate fy with respect to y, and we get minus 2x. And then we need the mixed partial, fxy. So here I'll take the partial of f with respect to x and differentiate that result with respect to y. And that gives us 1 minus 2x minus 2y. Okay. And I guess I should go ahead and check. I mean, this is a very quick thing to do to make sure that I did this correctly, because I mean these mixed partials should be equal. So the partial of f with respect to y differentiated with respect to x. And thank God they are equal, so that checks. All right. And we need these second order derivatives, partial derivatives, to compute D. That's the determinant of the matrix of second derivatives, which was defined as fxx fyy minus the mixed partial derivative squared. All right. So, all right, multiplying those, we get minus 2y for fxx, minus 2x for fyy, and fxy squared. Okay. So we're going to need to now test each of our 4 critical points in this determinant. But what makes this rather quick is that we're worried about not the actual value of the determinant, but rather its sign, right? So I like to use this table just to be organized for y'all. So I'll have a column with critical points. They were 0, 0, I believe. 1, 0, 0, 1, and the fourth one is 1, negative 1. Okay. So now I'll plug each of those into my second derivative, which is up here. Okay. And we're simply checking whether the result is negative or positive. So at 0, 0, you can quickly see that if x and y are both 0, we'll just get 0 for the first term minus a 1 squared. So that's a negative 1. Okay. So here I don't have to look at fxx, right? Because if the determinant there is negative, I know this is irrelevant, and I can right away say that I have a saddle. That our function f has a saddle at that point, 0, 0 in the domain. Okay. Alright, so we go on. And it looks like all these are going to be saddles, so. And ditto for the next one, so I won't bother. All right, and so now the determinant there at 1, negative 1. So let's see, we get the first factor is negative 2. The second one is positive 2, which is fishy that I'm getting all saddle points. I gotta... crap. Not good. Oh, that's a 5x, isn't it? Alright. Well, apparently I made a mistake, but I do have a solution, so this one is going to be wrong, by the way. Okay, so this is something went wrong here. Okay, I apologize, but I will give you the correct answer. I have it as the critical point I should have gotten is 1/3, 1/3. Okay, so if you want to check that on your own, I apologize. The other ones are correct, by the way. So, and this determinant at 1/3, 1/3 turned out to be positive, right? So I know I have a relative max or a relative min at that point. So I went to fxx. And what was fxx? Negative 2y. Right? So that's at this point. So that's going to be negative 2/3. Okay. So fxx is negative. And so just remember that's like concave down, second derivative being negative. So that's a relative max. So I can conclude that my function f has a relative maximum at this point. And if I need to know what value my function attains there, I would actually plug that critical point into the original function to find its value there, right? Okay. Well, that was somewhat... something's wrong. So that was somewhat a botched example that I actually worked out earlier. So oh yeah, to answer Rachel Mead, the stream will be archived, so if you want to watch it, I'll keep it up for a while. Or forever, whatever. But yeah, it'll be up afterwards. Alright. Alright, so do you have any requests? I was going to next do a Lagrange problem to review that procedure, but I will look at the chat if you want to request something right now. And Okay, well, I'll start with a rather simple Lagrange problem to just review the process, and then we can do a more complicated one, perhaps one with two constraints. Like there's one on your homework that's going to be similar. And then, yeah, let's do that. All right. So let me just... All right, so this is a simple Lagrange problem. So let's remind ourselves Lagrange is different. So it's like a constrained optimization because we'll have something we want to optimize, right? That's called our objective function, or it's called objective function many places. Right? We know it's our objective because it's the thing, it's the function that we want to optimize. So, for example, we might want to find we might be asked to find absolute max and min of the following function. Right? And again, you always want to, in a word problem, for example, you'll have to read from the context, obviously, what the thing is that you want to optimize and be able to write down the equation or the function representing the thing you want to optimize. Here it's just given. Okay, and then we're going to have a constraint. So let's say the objective function is some function of x and y, say. It could be more than two variables, obviously. Constraint is I'll write it as some function equal to a constant, right? So it's an equation, right? A level curve, if you'd like, of a function. And so that's the instructions would be find the absolute maximum of this function f subject to the constraints or subject to this equation. So here we're just going to the restriction is going to be that we must, the points in our domain are the circle given by the equation x squared plus y squared equals 1. Right? So in the xy plane, x and y can no longer be anything, but rather they must live on this unit circle of radius 1. Alright, and what was the procedure there? Well, the procedure was simply to find the gradient of your function f, your objective function, and set it equal to a multiple where the multiplier is conventionally given by the letter lambda for Lagrange. So maybe I should write Lagrange. So this is optimization using Lagrange. Right, Lagrange multiplier procedure here. That's what we're doing. And so it's the gradient of f equals lambda times the gradient of the constraint function, g. Okay, and then together with the constraint itself, we get a system of equations that have x, y, and lambda, and of course if we have more than two variables, maybe z as well. And we want to solve for critical points using this system. And I'm just going to be looking for xy pairs. Lambda might be interesting, but it's not I guess, relevant for us. All right, and then we simply plug those critical points back into the original function, right? In this class, we do not learn like a second derivative test for this Lagrange multiplier type of problem. It's simply find the critical points, stick that back into your original function to find your absolute maxes and mins. Okay. Oh, by the way, how do I know that? Why am I able to ask you for absolute maxes and mins? Well, the reason I'm able to do that is because you have a continuous function, and you'd like to, and it's constrained to a closed and bounded region. So the extreme value theorem guarantees that your function attains both an absolute max and min on that region, namely on this circle. Okay. So let's do this for this problem. Okay, and of course when I say the gradient of f, if you want to unpack that, it'll be just the partial of f with respect to x and y. And that would be equal to a multiple lambda of the gradient of g, and we recognize g in this problem as x squared plus y squared. So that's the partial of g with respect to x and y there, and the constraint itself. Well, in our problem this is 1. Okay, so let's write that out. Partial of f with respect to x we see is y squared minus 2x. And that should be equal to lambda times the partial of g with respect to x. Okay. Partial of f with respect to y, let's see. Where is it? It's 2xy minus 2y, and that's equal to lambda times the partial of g with respect to y. Okay. And that's our constraint. Alright, so it's this thing that we need to solve, the system for x and y. So one strategy here is to actually work with these two equations to get in order to get rid of lambda somehow, and then get a relationship between x and y. And once you have that relationship, go to the constraint in order to solve for x and y. Okay. So what can we do here? Well, we can do cases, right? Actually, I don't know what to do here, since it didn't write this problem. 1 second. Well, let's reason this way. Okay, is it possible? So is it possible that x is 0? So let's consider the case where x is 0. Okay. Well, if I look at let's call this equation 1, 2, 3. If we look at the first equation, if x is 0, then we get that y squared minus 2x equals lambda 2x. That just becomes y squared equals 0. So then we would get that y is 0. But why is that inconsistent? Why is that a contradiction? Well, this doesn't satisfy the third equation, the third constraint. The third equation, x squared plus y squared has to be 1, right? And that's 0. If x and y are 0, that doesn't happen. So this is, we get no solutions from this case, or no critical points. Okay, so now we can assume that x is not 0. Okay. Alright, so in that case, we can, for example, divide by 2x, correct? On both sides. So we get y squared minus 2x equals lambda times 2x, but I'll divide both sides by 2x in order to solve for lambda. And I can do that because I know that we're dealing with the case where x is not 0. So you can divide by x. So we get y squared minus 2x divided by 2x is lambda. Okay, and why did I do that? Sorry, I'll scratch that out. I want to do that because I can now replace lambda in the second equation, right? And that'll give me a relationship between x and y. All right, so here's the second equation. That's equation number 2. And now lambda becomes y squared minus 2x divided by 2x. And that's multiplied by 2y. And I'll just multiply both, after canceling this 2, I'll multiply both sides by x. Alright. Well, alright. And what can we do at this point? Wow. Oh man. Okay. Oh, that is the problem. All right. Let's see. What can we do? Well, is this good enough of a relationship here? We know that x squared and y squared, x squared plus y squared equals 1, right? Okay, this is definitely more difficult than I anticipated to solve the system. Let's see what are the answers. Oh, I know, there's a y over here. I forgot to multiply by y. So let's do that. X. Yeah, there you go. But that's even worse, right? Or is it? Okay, I know what I forgot, guys. It's right there. This y, it's still there. I just didn't write it. You can always chime in. Let me check chat. I don't have 2 screens yet for this, so I gotta... Yeah, and Shyla, we will we'll do a Lagrange multiplier with 2 constraints next. Okay. All right, distributing and no. Okay. All right. So now we see that this minus 2xy is on both sides of this equation, so you can add it to both sides and therefore cancel. And this will make the problem, I think, now tractable, right? I had this in my notes as a simple Lagrange multiplier, but I didn't bother to try it out beforehand. All right, so I brought everything to the right-hand side because we like to factor to see when stuff is equal to 0. So we can bring out a y. Okay, this might work out. Look at that. Okay. All right. Yeah. So this is the hardest part, right? Trying to solve for x and y here. But now we see that we have cases. We have the case where y is 0, and we have the case where y squared minus 2x squared rather is 0. So this means that y squared equals 2x squared. All right. Now, as advertised, now that we've have relationships between x and y here, I can now go to the constraint. I'll take this guy and then consider that constraint for both cases. So if you have x squared plus y squared is equal to 1, but y equals 0 in this case, we get x squared is equal to 1. Okay, so x is plus or minus 1. That's 2 critical points. Okay, so we have 2 critical points there. All right, case number 2. Again, we have x squared plus y squared is 1. But now we know for this case that y squared equals 2x squared. So we get 3x squared is 1. One second, I'm just going to double check something. Alright, so then we get x squared is 1/3. So now we have two solutions for x, plus or minus square root of 1/3. Okay. But of course we know critical points for this function whose domain is the xy plane. The critical points are xy pairs, so we got to go back here. Alright, so y squared is 2 times x squared, but that's just x squared is 1/3. So y is plus or minus square root of 2/3 after taking square root of both sides. Alright, so how many critical points does that give us? Well, it actually gives us 4. Let's list them. Okay, x could be positive 1 over square root of 3. And y could be independently negative or positive. So we have the positive version and the negative version. Alright. But x could also be negative square root of 1/3, and independently x could be positive or negative. So it looks like we have a total of, my goodness, 2 critical points from the first case and 4 critical points from the second. Okay, so what we're going to do with that, of course, is these critical points, stick them back into our function that we want to optimize, yeah? And just simply say that the absolute max happens where the function, where you find the max, and the min is where we find the min. So let's do that. Okay, so let's go through them. So the first critical point was 1, 0. So that becomes, that's negative 1. And we had negative 1, 0, which is also negative 1. And then the other points. So, and notice that the magnitudes of x and y for the 4 remaining critical points are the same. It's just the signs are different. So I can quickly change the signs in some of these. And another thing I can notice that we have x minus x squared minus y squared, which we know is 1, because we only chose xy pairs that are on that unit circle, right? So that'll always be 1. Wait a minute, that's positive right there. That's positive. That's negative. And that's going to be the same. Okay, well, that was sort of a mess, but we got them all, and clearly, let's see, so is this positive or negative? Can anybody tell? I'll use my calculator. It's going to be obviously negative, right? Because this factor is this term is smaller than 1. So it's going to be negative. But it's not going to be as negative as these guys. Okay. So I would say we have our maxes here. I'm sorry, our minimums. The function attains an absolute minimum of this amount at these two critical points. And this would be the maximum. If you check on your calculator, this would be the maximum. It's still negative, but maximum. And it happens at these two critical points. Alright. Wow. Alright. So let me read the chat real quick. Alright. Are we ready for a Lagrange multiplier with two constraints, perhaps? Alright, so let's look at two constraints. Lagrange can be extended to multiple constraints. So it's really in a form of a word problem, it seems. And here it is. So we're going to find the point on the intersection of the plane x plus y plus 2z equals 2, and the paraboloid given by the equation where z equals x squared plus y squared. Okay, so graphically, which is hard to do here for me, we have your paraboloid, and you have some sort of plane. Right. So here's the triangle the plane makes as it goes through, and it cuts the paraboloid at some kind of elliptic thing, and goes around. Okay, so that's like a probably an ellipse, right? I think going that's above the xy plane. So you just if I would have had more I could have had more time, I would be more careful here and draw it better, but all right. But we want to find the point on the intersection of those two surfaces, and notice that the intersection is a one-dimensional curve. It's an ellipse. That is, let's say, closest to the origin, right? Okay, so what's the function that I want to optimize? Well, the function I would want to optimize is, well, since we're looking for a point closest to the origin, we can optimize the distance function, right? So the distance function between a point, an arbitrary point in space, and the origin, 0, 0, 0. We all know that this is the square root of x squared plus y squared plus z squared. but we might have already learned that if you want to optimize distance, you might as well optimize distance squared. It'll just get rid of the square root. Let me just call that d squared. Yeah, for distance squared. And so our function that we want to optimize is distance squared. Squared just to make the algebra easier. Okay. So we want to, in fact, we want to find something that's closest to the origin, so we want to minimize this distance squared. So minimize this. And what are our two constraints? Well, we're looking for points that are common to both plane and paraboloid. Okay, sorry, I was just copying. So this function here is subject to these constraints. All right. Well, the setup won't be, using Lagrange here, the setup won't be too different. We have to take the gradient of the function we want to optimize, and we set it equal to a multiple of the gradient of the first constraint. So that's x plus y plus 2z equals 2, so gradient of g, plus another multiple of the gradient of the other constraint. And this is a good point here, right? We have to be able to write our constraint in the form some function of x, y, z equals a constant. Right? So if we have variables on both sides of the equation as we have here, we need to bring all the variable stuff to one side. So I would think of this as x squared plus y squared, and then minus z equals 0. Right? We just brought the z to the right hand side over here. So my h is x squared plus y squared minus z. Alright, so there we go. We have the gradient of the function we want to optimize f equals a multiple of the gradient of g plus a multiple of the gradient of h. Okay, that's the setup, and then using this we want to solve for x, y, z and make sure it's consistent with lambda and mu. Okay. Oh yeah, and our constraints, of course. Sorry. We also need to satisfy our constraints. And this is not an easy problem, right, necessarily, because could be a complicated system. But let's do it. All right. So we have f. It's distance squared. And so the gradient of f, if you parse that, is the partial of f with here's the gradient of f. Partial of f with respect to x, partial of f with respect to y, partial of f with respect to z. Okay, and that has to equal a multiple of the gradient of the first constraint. So equals mu. What's g? Where's g? Where's g? Where's g? Crap. Okay, let me just copy it. Let me just put it over here. Okay. So gradient of g is the partial of g with respect to x, partial with respect of g with respect to y, and z. Okay. Plus, as we said, a multiple of the gradient of the other constraint of h. Let me just stick that up here. So partial h with respect to x, respect to y, and with respect to z. Okay. And then we have the constraints themselves. Okay, and this is our system. Regarding the homework, so if they said if the instructions were to find the point, the highest and the lowest point of that intersection of the two surfaces, right? Then clearly, I mean, it's not absolutely clear, but from the context, I think it's clear that they mean the highest and the lowest z value, right? That intersection that we had over here was completely above the xy plane. And so when we think of the highest and the lowest point, they mean some point that has the smallest z value there, another point that has the highest z value. So the function you'd want to optimize there would be actually kind of funky. It's just z, right? Find the points on that intersection with the smallest value of z, the lowest and the highest value of z. So that's for the homework. Okay. Well, so how can we deal with this? What can we do? I would work with these equations first. These two. Oops. Why? Because I can easily solve for lambda in those two equations. Okay. So let's work with those. Let me just do this. So if I solve for lambda, I'm sorry, I can solve for mu in those equations. So if I solve for mu, in the first equation I get 2x, mu equals 2x minus lambda times 2x, yeah? And in the second equation I get mu equals 2y minus lambda 2y. Okay, and since mu equals mu, this tells me that 2x minus lambda 2x is the same as 2y minus lambda 2y. Okay, and then I would bring, let's say, all the terms that don't have a lambda to the left, and now I would just leave everything on the left side. Just bring everything to the left side, right? Because I think we can factor. I'll factor out a negative lambda from these two terms. Okay. And now we see that 2x minus 2y itself is common to both factors, so let's factor it out. Yeah, this is kind of tricky, I think. Okay, so this gives me two cases, no? we have that either 2x minus 2y is 0 or lambda is 1. Alright. And of course, for 2x minus 2y to be 0, it simply means that x must equal y. So I would say let's consider that case where x equals y. And then we can then do the case where lambda is 1. Okay. Okay, so if x equals y, I would go to the constraints at this point. All right. So we'll get that if x equals y, let's see, let's do the following. In the first equation, I'm sorry, this equation right there, and then we'll look at that equation. So in the star equation, of course we can replace y with x. Okay, so this way we see that z equals 1 minus x. Okay. But in the whatever that is equation, I can replace x with or y with x, and we'll get 2x squared equals z. And now we have two equations. And two unknowns, and we could try to solve, right? Z equals z. So this means that x squared equals 1 minus x. I did something wrong, didn't I? Z equals 2x squared. There you go. And that's a quadratic we're all familiar with, so I'll just use the quadratic formula for that. X is minus b plus minus square root of b squared minus 4ac. And that's all divided by 2 times a. Yeah, this is no fun. I don't think the problem on your homework is fun either. Maybe it makes it easier because the function you're minimizing and maximizing is pretty simple. It's just f equals z. But oops, what am I doing? All right, so x could be 1, or x could be negative 1/2. What did I do wrong? All right, this. Let's just be careful here. Z equals 1 minus x. Z equals 2x squared. Alright, so we brought this over here. That's a plus. So that's minus. So that's minus. It's minus. Slight mistake. Alright. So, in fact, x is either negative 1 or when we have negative 1 plus 3, that's 2, or x is positive 1/2. That's better. Oh boy. Okay, yeah, that's not easy. If x is -1, what is y? Well, remember we're dealing with a case x equals y. So y would be -1 as well. And then what is z? Well, either one of these equations will tell me that x is -1, z is 2, and it's consistent. Like both of those equations give me the same value of z. Okay. And that's going to be, yeah, that works out. Cool. All right. Well, that's one critical point. Yay. I think we're doing okay. So what was the other case? X is negative or positive 1/2, I should say. In which case, since x equals y, y is positive half, and either of these equations would give me that z equals 1/2, and both of those give me that value, so that's consistent. So that's another critical point. Alright, so we got two of them. Is there a case I'm leaving out? We better scroll up. I think we are, right? Okay. We had the case where x equals y, but we still have to consider the case where lambda equals 1. Oh boy. This is not a homework question. This is more like a project, you know? All right. All right. I just copied that system really quickly. Get out. So yeah, we wanted to consider the last case where lambda is 1. So let's do that. Let's see. So if lambda is 1, okay, I see it. Okay, I'm looking at the very first equation over here, and I'm just going to simply replace lambda with 1 and see what happens. Well, 2x it can be subtracted from both sides, which would give me that mu is 0. Okay. And you would get the same information from the second equation. So then we can go to the third equation, and we get that 2 times z equals 2 times 0 minus 1. And why is this a contradiction, by the way? Z equals negative 1/2. Negative 1/2. Because remember, we have to satisfy all equations, all 5, including this one, which tells me that x squared plus y squared is a positive z, right? Or non-negative z. X squared plus y squared is never negative, so it's impossible that z is negative. According to this last equation. So this case yields no solutions. So no solutions from this case. Wow, alright. So, okay, no solutions. So we only have 2 critical points. We can now do what with them? We can stick them back into the function we wanted to optimize, yeah? Let me pull them, rewrite them. Oh, I'm out of paper. 1 second. Let me just do pixels. That doesn't look right. Well, let me just write over the scrap. There you go. And Alright, what was our function? Okay, we had our function was distance squared. So we simply need to evaluate our function. I wanted to, in our case, minimize because we wanted to find the closest distance. We want to evaluate it at these 2 points. Yeah, so that's what? Four, 5, 6, yeah. So we get a quarter, and that's 3/4. So clearly the function has the smaller value of 3/4 at 1/2, 1/2, 1/2. So that would be the point on the intersection of the paraboloid and plane that's closest to the origin. Yikes. So here's the point. We found it. And if they had asked for the actual distance, we have to remember that our function was distance squared, so its distance from the origin would be the square root of distance squared, yeah? All right, well, cool. Okay, so let's see, so that was a constrained optimization, 2 constraints, so it was a hard Lagrange. But let's look at one more type of thing, that's optimization, where we have our function being constrained to a region in the plane. So it's not just a curve. It's not your constraint is not just an equation, but it's an inequality, right? It's a whole region. So we'll remind ourselves of the procedure for that. All right. So this is what I mean. So we want to find the absolute max and min of the following function, our objective function, because it's the thing we're optimizing. All right, that's a y. Darn it, that's a y for sure. Okay, but we want to restrict this function to be on this, I guess, elliptic disk. So it's going to be we're restricting ourselves to the region in the plane which satisfies this inequality. Okay. Right, so notice it's an inequality. It's not a strict equality. So if we just had, that we're looking at our function on this thing, so that would be an actual ellipse. It's a curve. So then we can go straight to Lagrange. But we're also considering the interior of the ellipse. If you want to, I'll try my best to draw this here. So we have an ellipse with, it kind of looks like, oh wait a minute, this is paint. It has shapes. I don't ever use paint. Alright, this has shapes after all. Whoa. Oh my gosh, okay. That's the x-axis, by the way, and that's the y-axis. All right. Right, so the equality would just give us the boundary, that's just the ellipse. But since we have the inequality, our region is the ellipse plus everything interior to it. It's all that stuff. That's why I called it an elliptic disk. That's D, right? So what we want to do here is first first consider the interior, right? So this is where we want to consider the interior of D and find all critical points on the interior, or in the interior, sorry. Well, however way you want to visualize that. Okay, so this is kind of like the unconstrained case, where you simply take the partial derivatives of your function, set them equal to 0, solve for critical points, but only consider the ones on the interior, or in the interior. Right, we could have other critical points outside, right, which would be relevant to our region. Yeah, we just want to consider the critical points on the interior. All right, so it's like an unconstrained case optimization problem. Okay, so where's my function? There it is. So here's my function, and I'm doing the first part, where I'm just finding critical points and keeping the ones that are inside my region of interest. We set that equal to 0. Partial left with respect to y, set equal to 0. And then we solve the system, so we see from the first equation that x must be 1 and y must be, I believe, let's see, y must be 6/4, so 3/2. So that's a critical point. But is it inside our region of interest? Is it inside of in region D, as we called it? So how do we check? Well, we simply check whether that inequality holds, right? Whether our point satisfies this inequality. Because if it does, it's inside our region. So this is our constraint. And I'm just going to simply check whether this inequality holds at our critical point. So 3 times x squared, so that's 1 squared, plus 2 times y squared. Let's see, that's 3 plus 2 times 9/4. Well, whatever that is, it's definitely less than 15, right? This is 7.5. That's definitely less than 15. So our inequality holds. We are inside of D. So we found a critical point inside of our region of interest. You can even 1 and 1.5. So let's just put it, it's 1 and 1.5. It's somewhere over here, right? That's a critical point. Okay. So step 2, right? We found all the critical points on the interior of D. So now we go to the boundary for step 2. And this is where you get to use Lagrange multipliers. Oops. So now we look at the boundary. So this is where, okay, 3x squared plus 2y squared equals 15, right? It's like just the equality part which gives us the boundary. Okay. And you find critical points there. All right. So for what technique would we use there? Well, clearly Lagrange, right? Because Lagrange can be used when you have a constraint for x and y given by an equation, yeah, equality equation. So we have this chunk. Let me just copy this. I just need this reference. Okay. So again, Lagrange, we have the gradient of our function that we want to optimize, f, equal to a multiple, our Lagrange multiplier there, gradient of the constraint, where the constraint clearly is, right, 3x squared plus 2y squared. All right, so again, so gradient of f should be equal to a multiple of the gradient of g. So 6x 4y. And together with the constraint itself gives us a system of equations which we would like to solve for x and y. Alright, so let's solve. So this is an example again where I'm going to be working with these two things first and then going to the constraint to solve for something. So let's see. Okay, is it possible, if you look at the first equation here, is it possible that x is 0? Well, if it were, what would happen? If x were 0, you would get 0 minus 6 equals, lambda times 0, so 0. Well, you would get that 6 equals 0. So there you go, not possible. So x is not 0. And for the same reasoning, if you look at the second equation, you can quickly reason that y cannot be 0, because if it were, you get 6 equals 0. So no, no. Yeah, no and no. So neither x nor y are 0. We can divide by x and y, right? Okay. So looking at the first equation, I can divide both sides by 6x in order to solve for lambda. And I can do the same for the second equation. Divide by 4y, right? And I'll simplify. I'll simplify here as well. Now, what am I doing here? Well, okay, because lambda is the same thing as lambda. I can set these equal to one another and again get a relationship between x and y. So x minus 1 divided by x is the same as 2y minus 3 divided by 2y. And I'll cross multiply. And these two terms cancel. And we get the 2y equals 3x. Or if you'd like, y is 3/2 of x. Okay, so that's a relationship between x and y, which I can now take and use it together with my constraint. Okay. Where y is 3/2 of x, so 9/4 of x squared. Oh, behold, x squared is 2. So x is plus or minus square root of 2. Alright. So if that's x, I guess what's y? There's the real y is 3/2 of x. So y, plus or minus 3 times square root of 2 over 2. Alright, so that gives me 2 critical points on the boundary, right? We get x is positive square root of 2, in which case y has to also be positive, 3 times square root of 2 over 2, or x is negative, and so y would also be negative. Okay, so those 2 critical points, if we scroll up, are kind of like kitty corner to one another, right? So they're over here. Don't know exactly where, but we can surmise the one's over here. And the other one is kind of like in the opposite. Alright, but anyway, you would have these 3 critical points, and because it's 4:38, well, we have 5 minutes, but, you take your 3 critical points and you simply evaluate your function there, right? And then the maximum value is the absolute max your function attains, and the minimum value is the absolute min. So, I guess, does anybody have anything in chat, anything specific? This is your chance. Alright. And there's those are the last 2 sections. There's also directional derivative, chain rule, tangent planes, and linear approximations, limits and continuity. But if nobody has any objections, I guess I'll end it here. Alright, well, thank you guys, that was great. This was my first experience with it, so I appreciate the patience. Thanks. Bye.